Okay, so in this video, we are going to discuss about tree-based methods. I'm not sure how familiar you are with this method. Some of you might have heard about this. Some of you might have done some analysis using decision tree or regression tree or classification tree, whatever you call it. But I would say that for some of you, this might be a totally new thing that you have never done before. So let us just go to the basic of tree-based methods and what does it mean. Okay, so in the previous class, we have covered two different, uh, actually we have covered a few, but basically we have covered linear regression, which I'm sure you're all familiar with. And we also have classification analysis, in which the main thing in classification analysis is the logistic regression, which some of you are quite familiar with. But this tree-based method is a new thing and it is totally different from the two that we have covered previously. So these tree-based methods, it can be used for both classification and regressions, depending on the value for your response variable. So let's say you have a numerical response variable, then we're going to have a regression tree. But if you have a response variable which is in categorical, then we use classification tree. But basically the method is the same. It's just that if you have different type of response variables, the way you interpret the results and the way the tree is structured is going to be different. So how about categorical response? Can you have more than two categories? Like in the logistic regression, we can only have two categories. Y is equal to 1 or Y is equal to 0. Y is equal to A or Y is equal to B. But for tree-based methods, we can have more than two categories. Okay, but of course not too much, because then it becomes very complicated. So the most distinctive thing about decision tree is the splitting rule. So splitting rule, what does it mean? Okay, the word split. The word split also, it means that we stratify or we segment or we group. Okay, we make a distinct group, we make a different segments, we make a different stratification based on the predictor space. Okay, this predictor space is the predictor variable, the x variable, the space in the x variable. So let's say if x variable is categorical, like male and female, then we make a distinct segments based on whether this is a male or whether this is a female. Okay, because it might be that maybe you are interested in looking at who is more likely to buy certain kind of product. Okay, and it might be that majority of the female are more likely to buy this product compared to male. So that is how you make a distinctive segment. And if the predictor, or if the x variable is numerical, like x variable is age, then you're going to make a segment based on a certain cutoff value. For example, like people are more likely to buy this stuff when the age is lesser or equal to a certain age. All right, so that is the predictor space. So we divide this predictor space into different segments or into different stratification, and we divide this into what we call as the simple regions based on the mean or the mode. Of course, if the predictor variable is categorical, then we base on the mode. If it is numerical, then we base on the mean. So people, the tree-based methods is popular because it is simple and it is very useful for interpretations, because it mimic the human decision process. So you start from one thing and then you go to another. For example, like if you asking yourself a 20 questions game. Okay, so first is, where do you want to go? You want to go to a city, or you want to go to the to the rural area? And then if you choose rural area, then you ask yourself, okay, you want this type of vacation or another type of vacation, and then you go down that lane. All right, so it is very useful for interpretation. However, it is typically not competitive with the best supervised learning methods, especially the more complex ones. But if one decision tree is not competitive with the best supervised learning methods. We can, however, produce multiple trees. So instead of having just one tree, we can use many techniques such as bagging, random forests, and also boosting to combine multiple trees to increase the performance of the model, to increase the predictive accuracy of the model. However, when we combine multiple trees, it will increase the accuracy, but we're going to have some loss in the interpretations, because if you combine many trees, it's sometimes it is almost impossible, or it will become very extremely difficult to actually interpret the results, okay, compared with having one tree. So let me just show you how a decision tree looks like. So this is a very simple one, and for this one we use HITTES data. If you want to learn more about this data, you can go to the main textbook, you can read more. So basically this HITTES data containing information on the salary of the baseball player. We also have information on the number of years that he has played in the major leagues, and also the number of hits that he made in the previous year. So what we are going to try to predict is, we want to predict the salary of this baseball player based on the number of years of the experience, how long he has been playing in the major league, and also the number of hits that he made in the previous year. So two predictor variable and one response variable, and this response variable is numerical. And we use log salary instead of salary, because salary is usually very highly skewed. Okay, so we use log, so it looks more like a normal distribution. So based on this data, we apply the regression tree, okay, because the response is numerical, and this is the resulting output. We have a decision tree on the left here. So the decision tree suggests to us that the most important variable is actually years of experience. Okay, so let's say if the number of years that he has played in a major league is less than 4.5, then we would expect that his log salary is equal to 5.11. And because this is a log value, so the actual salary is the exponent of 5.11, which is equal to $165,000. Okay, so this might be you know, a year or based on a month. I'm not really sure. We have to go back to the data set. And obviously what we see here is that if you have less years of experience, your income is going to be lesser compared to if you have more than 4.5 years of experience. You can see that on the right branch here, we have two level of income. We have 6, and we have 6.74, which is much higher than the left branch here. Okay, but on the right branch we have another node. So this is what we call as node. We have another decision to make. So this is based on if he has a longer years of experience, and then we look at another thing. We look at the hits that he made in the previous years. If he made more hits, then his salary is going to be higher. If lower than 117.5, his salary is going to be lower. Okay, so how do we make decisions based on this 4.5 and 117.5? Do we actually introduce, do we actually tell R to, divide the year at 4.5 and divide the hits at 117.5? No, definitely not. Okay, so this number is actually derived from the decision tree algorithm that we are going to discuss later. Okay, so basically, let's talk about the structure of this decision tree. We can say that this tree has two internal nodes. Okay, the two internal nodes is one at the years here, the splitting at the years, and another one, the split at the hits here. Okay, so this is internal because they are not terminal nodes. We have three terminal nodes here. One is the income here, 5.11, another one at 6, and the last one is at 6.74. So we can say that the size of our decision tree here is actually equal to 3. Okay, so this is how the regions look like. If we go back to here, okay, if we look at the definitions of the splitting rule, we say that we stratify or segment the predictor space into a number of simple regions based on the mean or the mode. Okay. So this is what it means by different regions. And because we have 3 terminal nodes, we have 3 regions here. If you have like 17 terminal nodes, you're going to have 17 regions here. Okay, so the first region is R1 here. So the first region is divided by the years. Okay, so here we have the year from 1 to 24, and the splitting is made at 4.5. So first is you divide the regions in 2 segments. One is if the years is less than 4.5, and the other one if the year is larger than 4.5. Okay, so this becomes the first region. And based on the remaining region on the right hand side here, and then the second splitting is made based on the number of hits. Okay, so based on this particular segment, we divide the regions into 2. One is if hits is less than 117.5, and then another one if hits is larger than 117.5. So here in the resulting output, we have 3 segments. We have 3 regions. Okay, so for the R1, we would expect that the log salary is 5.1, or the salary is equal to $165,000. So this is, if you want to know why I multiply with 1,000, this is because the data that we have in this data is actually in thousands. So that's why we multiply with 1,000. Okay. So you can read more about these data sets in the textbook. So this is the 3 regions, the 3 resulting regions. For if any individual falls into any of these 3 regions, it is easy for us to actually predict what would be his salary. Okay, so now let us discuss the process of building the regression tree. So it involves 2 steps. Number 1 is we divide the predictor space, which is the set of all possible values for x1, x2, and all the predictors that we have, into j distinct and non-overlapping regions, R1, R2 until Rj. Okay, so in this case we have 2 x variable, x1 and x2, so we can actually put it into this scatter plots, years and also hits, and from here it's easier to see because we only have 2 variables. And then we divide into j distinct and non-overlapping regions. So here we have 3 distinct and non-overlapping regions. Okay. And for every observation that falls into the region Rj, we make the same prediction, which is simply the mean of the response value for the training observations in Rj. So what it means here, for each of the individual dots that you see in R1, for example, we would predict that everybody's salary is going to be, $165,000. For everyone in region 2, we are going to expect that the salary is equal to the mean, which is $402,000. But this is because the response variable is numerical. What if the response variable is categorical? Then we will base on the mode. Okay, the mode is also the highest occurring class. For example, like you have 3 categories. You have A, B, and C. And for the second region, the highest occurring class is actually belong to B group. So you would expect that everyone that falls into the second region would be B instead of A and C. Okay, let's take this example just to show you on how the algorithm work. Suppose that in step 1 we obtain 2 regions, R1 and R2. In the previous example I show you we obtained 3 regions, but now just to bring you to these steps. Suppose that we have 2 regions, R1 and R2, and the response mean of the training observation is for the first region is 10, and the response mean for the training observation in the second region is 20. So for any given observation, if x belong to the first region, we would predict that the value for this x is equal to 10. And if it belongs to the second region, we would predict the value of 20. Okay, so now the question comes to mind. How do we construct regions in R1 until Rj? And how do we know how many regions for us to construct? Okay, if we have two variables, how many regions? If we have more than two variables, how many regions are we going to end up? Okay, so this is not actually really depends on the number of variables. It doesn't mean that if you have two variables, you're going to end up with 3 regions. If you have 5 variables, you're going to end up with 10 regions. It's not like that. Okay, it depends on the purity of the nodes that you're going to have. Okay, just like in the linear regression, we base on the least squares methods, where we try to minimize, we try to find the beta coefficients that can minimize the the sum of squares of the errors. So what is the the basis of constructing the decision tree? So in theory, the regions could have any shape. It is not supposed to be just like a square. However, we choose to divide the predicted space into high dimensional or rectangles or boxes for simplicity and for ease of interpretations of the resulting predictive models. Okay, because if you do not have a rectangles or boxes, it's going to be quite very difficult for us to actually visualize it, and for us to actually divide the regions into into a proper segmentations. So the goal is to find the boxes of the regions that minimize the residual sum of squares. Okay, so this look like just like the linear regression that we have covered in the previous lectures. We have the actual y, and we have here the y hat of Rj, where y hat of Rj is the mean response for the training observation within the J's box. So what we are trying to do here is, instead of having the actual y and the predicted y, well, in some sort of way, this is also, a predicted y. The y hat is actually predicted y. But in the decision tree, it's more like this is the predicted mean value of the y. Okay, so we try to minimize the actual value of y with the mean of y in that particular region. Okay, so we want to find a region where the observations are more close to each other, are more similar to each other. So this is the basis of constructing the region in in a tree. Okay, however, if we try to do this manually, it is computationally infeasible to consider every possible partitions of the feature space into J boxes. Imagine if you have to, using our HITES data just now, you're trying to find a segmentations based on years equal to 0.1, 0.2, 0.3 until 1 years of experience, 2 years of experience, 4 years of experience, and so on. Okay, so that is just based on one variable, and then you have a second variable, a second predictor, which is the number of hits that he has made last year. Okay, so it is computationally infeasible to consider every possible partitions of the feature spaces into J boxes. So what we do is we take a top-down, a greedy approach that is known as recursive binary splitting. So this is what the decision tree algorithm is called, the recursive binary splitting. Okay, the greedy approach means that, what does it mean, a greedy approach? Okay, a greedy approach means that it begins at the top of the tree, at which point all observations begin to a single region. Okay, so now imagine that you have all the variables in your hand now, and you want to make the first split. Okay, so here we are at the we begin at the top of the tree. Okay, we make the first split, and then after the first split, we make a successive splits after that, and we go on until we stop at some stopping rule. Okay, so each split is indicated via 2 new branches further down the tree, and this method is called greedy. Okay, what does it mean? What does greedy means? Okay, because at each step of the tree building process, the best split is made at that particular step. Okay, rather than looking ahead and picking a split that will lead to a better tree in some future steps. So if you play chess, we would say that the greedy approach is something like this. You don't care about what is the next step. You do what is best for now. You move your pawn. You move your pawn based on what you think is the best for now, without having to think about what would be the consecutive. So when you make a greedy, when you split based on a greedy approach, so in the first split, you're going to look at all the predictors that you have, and then you find that, oh, this is the most significant, this is the most important variable, and you choose, for example, like the most important variable is x1, and then you choose x1. And after you split into two based on some threshold value t1, and then you look at the left branch, if you find that, oh, I have based on all predictors here, including x1, what will be the next important variable that can split this data, okay? And then you find that x2 is the most important variable at the left branch here, and then you split, okay? And if you go further down, you find that, oh, we do not have enough observation anymore, or none of the predictor variable become significant anymore, so you stop. And here on the left branch, we have two regions, R1 and R2. Okay, so let's look at the right branch here. So in the first branch, at the top, you have x1. And in the second one, you still have x1. So this is possible, okay? Because after you split the value, or after you split this predictor into two, and you go to the next step, and then you ask, what is the most significant variable here at this point, and you find that x1 is still the most significant variable here, so you choose x1, and then you split again until you arrive at a certain point where you think none of the predictor becomes significant, and then you stop. So in this example, we have 5 regions, so we would say that the size of 3 here is equal to 5, and this is how the the regions look like. And here we have, instead of 2 dimensions, now we have 3 dimensions, because we also include the value for y here, okay? So you can see that the lowest y is when we have a high x2 and a low x1, which is the first, the first region here. You might not see. And then so on. So this corresponds to the value of y also, right? So now let's talk about the tree pruning, okay? So if we produce a very large tree, okay, if we look at the previous example like this one, this is a very simple tree with the size of 5. I would say that this is the a very small size of a tree. Sometimes when you have a very complex data set, you're going to have a very large tree. And a very large tree might be too complex. It may overfit the data, leading to poor test performance. So I like to use the analogy of, sewing a shirt, for example. If you sew a shirt just for yourself, based on the length of your shoulder, the length of your arm, and the length and your and your hips and everything, so if that cloth is really fit to your body, then I'm afraid if you try to fit this cloth to another person, it's not going to be a good fit anymore. Okay, so that is the analogy of this. If you build a model that is too complex, okay, you try to capture everything in the data, then I'm afraid we're going to overfit the data, leading to poor test performance. Because when you have a training data sets and the testing data sets, these are 2 different data sets, okay? You build the model based on the training data sets, and when you try to test it using the testing data sets, it's not going to perform very good, okay? So that is why we want to have a medium size of a tree that is not too complex, but not too simple, of course. We want to try to capture the data, the relationship between data, but we do not want to have a model that is too complex. So a smaller tree with a fewer splits might lead to a lower variance and better interpretations at the cost of a little bias. Okay, so again, I want to talk about this variance and bias. Okay, so if you have a very complex model which perform the best on the training data sets, okay, it can capture all relationship in the training data sets. But when you try to fit this model using the testing data set, it might not perform very good, okay, because you overfit the data. So in this case, we're going to have a higher variance, okay, because there is a huge difference between the model performance in the testing data sets and also in the training data sets. Okay, now let's talk about bias. Bias is the ability of the model to really achieve highest frequency, highest accuracy. Okay, if you have a model that is too simple, you're gonna have a risk of having a higher bias. Okay, if the model is too simple, it's not able to really make an accurate prediction, then we're gonna have a bias. But as you increase the model complexity, you're gonna have a little bias. But when you have a high bias, you're gonna have a high variance. Okay, because if you build the model too complex, sorry, maybe I want to talk the other way around. Okay, if you build the model too complex, you're gonna have a little bias because you can increase the accuracy, but you're gonna end up with high variance. But you have a model that is too simple, you're gonna have a high bias, but you're gonna have a lower variance. So there is always a trade-off between the two. Okay, so there's no really a specific rule on what is the value of the bias and variance that we should choose. Okay, so that is why we should compare between many models to find which one is which one is good enough but not too complex that it overfit the data. So between a very large tree and between a very small tree, okay, that we're gonna end up with high or low bias and variance, what would be the solution? Okay, what would be the best way to build a decision tree? Okay, the solution is we should build the tree so long as it decreases the residual sum of squares exceeding some threshold value. Okay, but this can also be short-sighted. A seemingly worthless split early on in a tree might be followed by a very good split. Okay, what does it mean? Because remember, we use a greedy approach. So at the top of the tree, you look at all the predictor and you think that, oh, x1 is the most important variable here, so I choose x1. And after that, we move on further and further down without having to look back at the what we choose earlier on. But it might be that, instead of choosing x1, if, who knows, you choose x2, okay, at the first split, and then you go on and go on down the road, okay, and you find that overall, the model choosing x2 at the top of the tree actually performed better than the model that actually choose the most important variable in the first split. Okay, it might be that. So the best strategy is to grow a very large tree, which we call T naught here, and then we prune it back in order to obtain a subtree. So we grow a very large tree and then we prune. Prune is we cut down some of the branches of the tree. So now we grow a very large tree and then we prune it back in order for us to obtain the subtree. Okay, a subtree that is simple enough for interpretations and not too complex, but it is useful. It's not too simple. It is still useful to explain about the relationship in the data. So the question is, how do we determine the best way to prune the tree? Okay, where to prune the tree and how much do we want to prune the tree? So intuitively, we would say that our goal is to select a subtree that leads to the lowest test error rate. Okay, so let's say we have a subtree here. What we can do is we can estimate the test error using cross-validation or the validation set approach. Okay, but you need to remember there might be an extremely large number of possible subtrees. Okay, if you have a very large trees, you might have branches here and there, and there's so many possible number of subtree. So estimating the cross-validation error for every possible subtree would be very cumbersome. Okay, so we need a way to select a small set of subtrees for our consideration. So here we can use the cost complexity pruning. It is also called as weakest link pruning. Okay, so this gives us just a way to do this. So rather than considering every possible subtree, we consider a sequence of trees indexed by a non-negative tuning parameter alpha. So let us talk about this alpha, right? So I'm going to talk about this first, and then we're going to explain what does it mean. Okay, so for each of the value of alpha, there corresponds a subtree T, which is a subset of T naught. Remember that this T naught is actually a very large tree that we grew. Okay, so T here is actually a subset of T naught, such that, okay, so this is the sum of squares of y minus the y hat Rm. The y hat Rm is the predicted response or the mean of the training observation in these particular regions. Okay, so we try to minimize this value of y and the mean of the y in that particular region. We try to minimize it as much as we can. But here, so if you look at the first part of the equation, it looks similar to the previous one that I'm just going to show you, this one. Okay, so this is the goal, or this is the basis of minimizing the RSS to find the regions in the decision tree. But now we have a second part here. The second part containing the alpha and also the absolute value of T, where T is the number of terminal nodes of the tree. Okay, so what is the terminal node? I'm going to show you again. Some of you might just forget. So this is the tree of the size 5 because we have 5 terminal nodes here. For the HITAS data, we have the tree with the size of 3 because we have 3 terminal nodes here. Okay, so that T is actually the size of the tree, or the terminal nodes of the tree T. Okay, so what does it mean here? It means that we try to minimize the residual sum of squares here on the left part, but with some tuning parameter on the right hand side. Okay, the tuning parameter is A multiplied with the number of terminal nodes. Okay, so this tuning parameter alpha, it controls the trade-off between the subtree's complexity and its fit to the training data. So the subtree complexity is given by T, because the higher the T, the higher the terminal node that you have, you're going to have a higher model complexity. And on the left part, this is the fit to the training data. How fit the model is to the training data. The lower it is, the better the fit. Okay. So when in other words, if alpha is equal to 0, then you're going to end up with T naught. Okay, because there's only on the left part here, because on the right hand side it is 0. Okay, but if you try too hard to reduce this residual sum of squares, okay, you're going to end up with a high number of T. So that is why if you have a high number of T here on the right hand side, it's going to be penalized on the whole model performance. So the inclusions of alpha and the absolute value of T here is going to choose something, okay, that can minimize the left hand side part while it stabilizes the number of the terminal nodes that you have. Okay, you're not going to end up with a model that is too complex. So let me explain to you the algorithm behind building a regression tree. Okay, so the first step is we use the recursive binary splitting to grow a very large tree on the training data. We only stop when each terminal node has fewer than some minimum number of observations. And most commonly, minimum number of observations that we use is n equal to 5. So when at some terminal nodes, when you have n equal to 5, you no longer do the splitting. Okay. And then we apply the cost complexity pruning to the large tree in order to obtain a sequence of the best substrate as a function of alpha. So we do this, we run these equations, okay? And then we use the k-fold cross-validation to choose the value for alpha, which is we divide the training observations into k different segments, k different groups, or k folds. And for each of the groups, 1, 2, 3 until k, we repeat step 1 and step 2 on all but the k-fourth of the training data. And then we evaluate the mean squared prediction error on the data in the left out k-fold as a function of alpha. And then we average the result for each value of alpha, and we pick alpha that minimizes the average error. And we return to subtree from step 2 that corresponds to the chosen value of alpha. Okay. So this graph actually shows example of how to choose the right size of the tree. So you can see that the horizontal axis here is actually the tree size. As you increase the size of the tree, as you increase the number of the terminal nodes in the tree, you can see that the mean squared error for the black curve, which corresponds to the training data sets, actually reduce. Why? Because as you increase the complexity of the model, as you increase the number of the terminal nodes, as the tree grow larger, you're going to have a lower MSE. But here we also run the cross-validation, which is shown on the green curve here. And also we have the testing error rate here. As you can see, actually, if you look at all three of them, the minimum one is when the tree is equal to the size of 3. Okay, the size of 3 here. So if you go to 4 terminal nodes, as you increase the tree size, you can see that the MSE for the cross-validation and for the testing data sets actually increase. So we say that the optimal number of the tree for this HITTES data is actually 3. Okay, THREE. Okay, so now we have done our discussions on the regression tree. How about classification tree? Okay. So a classification tree is very similar to regression tree, except that it is used to predict a qualitative response. So when you have a response variable in category, then we use classification tree. But basically the way you grow your tree and then you do the cross-validation is the same. So in this classification tree, it predicts that each observation belongs to the most commonly occurring class of the training observations in the region to which it belongs. So as you can see, in the regression tree, the terminal nodes contains the mean of the response variable, but in the classification tree, the terminal node should contain the most commonly occurring class. So in interpreting the results of a classification tree, we are often interested not only in the class prediction corresponds to a particular terminal node in region, but also in the class proportions among the training observations that fall into that region. So in other words, in the terminal node, we are not only interested in looking at whether, after splitting this and that, whether we're going to have A or B or C, but we are also interested in looking at the proportions. For example, that if this particular terminal node, we would expect that it becomes B instead of A and C, we will also want to know what is the proportions of B in that particular terminal node. So the proportions of 80% and the proportions of 50% are different, because with the proportions of 80%, you're pretty sure that this observation belongs to B. But with the proportions of 50%, you can say that the majority is B, but you're not really sure about that. So in the classification trees, you're not able to use RSS because RSS for numerical. And so for the binary splits, we will use a classification error rate. But if you look at this one, okay, so this is the classification error rate. It's given by E equal to 1 minus the maximum of the P hat of MK. So the classification error rate is simply the fraction of the training observations in that region that do not belong to the most common class. So for example, let's take three categories. Okay, we have A, B, and C. Okay, so if we would expect that for this region, everybody will be B, where B is the most commonly occurring class. So E actually is the proportions of those who are not B. Okay, so the P hat of MK represents the proportions of the training observations in the mth region that are from the kth class. Okay, so however, classification error is not sufficiently sensitive for tree growing. So that is why we use the Gini index and the other one, which is the entropy. Okay, so this classification error rate, it might be insensitive. It might be insensitive for the tree growing. So in the practice in building the classification tree, many researchers have used either the Gini index or the entropy index. Okay, so let us look at the Gini index first. So this Gini index is equal to G equal to the sum of P hat MK multiplied with 1 minus P hat MK. So this Gini index is a measure of total variance across the case classes. So it takes on a small value if all the P hat MK are close to 0 or 1. And this is referred to as a measure of node purity. Okay, now let me take you to this equation and what does it mean? Okay, so if you look at the classification error rate here, you have E, where E is equal to 1 minus the max of P hat MK. Okay, so this one, if you look at the classification error rate here, so this is, you try to maximize the P hat MK here, okay, and the error is just 1 minus this max of P hat MK. What it means is that if you know that this region contains mainly of B, then the error rate is actually the proportions of the observations that do not belong to group B. Okay, but if you look at the Gini index, this is between those who are in group B multiplied with the proportions of those who are not in the group B. So if you have a small value of the Gini index, it may indicate that the node contains predominantly of observations from a single class. So the Gini index allows us to obtain a node purity, the informations of the purity of a certain node. For example, if this terminal node contains purely or have a higher purity for those belonging to group B, then the value for the Gini index here will be lower, okay, compared to those having majority of B but also the proportions of the other groups are also high, then it is not really pure. So we would say that for this one, we would expect that the Gini index will be higher. Okay. So alternative to the Gini index is the entropy, which is also a commonly used criterion in classification tree. So the entropy is given by D equal to minus of the sum of the P hat MK multiplied with the log of P hat MK. So since why we use this value P times log of P, because the value of the P hat MK is always between 0 and 1. Okay, so the entropy will take on the value near 0 if the P hat MK are all near to 0 or all near to 1. So this is between purely 0 or purely 1. Okay, so if the P hat MK are nearly 0 or is nearly 1, which shows some purity there, then the entropy will take on the value of near 0. And that is what we intend to have. Okay. So the Gini index and the entropy are quite similar numerically. So it is not surprising if you actually find a similar results between the two. So the Gini index and the entropy are more sensitive to node purity compared to the classification error rate. So hence they are typically used to evaluate the quality of a particular split. So in summary, I would say that any of these three approaches might be used when pruning the tree. However, after you prune the tree and you're satisfied with the pruned tree, with the tree that has been pruned, and you want to get the prediction accuracy of the final pruned tree, then you can use the classification error rate, because in the final pruned tree we are interested in looking at how many have we correctly classified and how many that we have misclassified. Okay, so I give you another example. So this one is also the data which is from the textbook, and this is, as you can see, this is a full grown tree. So we, if you compute here, I'm not really sure, but we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18. So here is the size of 18. We have a classification tree, because obviously if you look at the terminal node here, instead of having numbers, you have categories. So you either have yes and you have no. Okay, and this is a classification tree, and we have the size t is equal to 18. So for this particular data, when we try to do the when we compute the error, remember, this is not MSE, this is the error rate, because this is obviously for classification problems. You can see that for the training data, again, the error rate reduced if we increase the tree size. However, you can see that after the size of 5, starting from 6 and above, the error rate for the testing and for the cross-validation actually increased. So here we can say that the optimal number of the tree is actually 6. Okay, sorry, it's not 5, it's 6 here. So after we prune the tree, we have decided that the optimal number of the terminal node is 6. So we end up with this pruned tree, where you can see that you only have like 6 terminal nodes here. So now we want to compare between the decision tree and the linear models, and we want to know which model is actually better. So it depends on the problem at hand. So on the left part here, I show you the equations for the linear models, where we have beta naught plus beta jxj, and on the right hand side, this is the equation, one of the equations for the tree models. So if the relationship between the features and the response, or if the relationship between the x variables and the y variable is well approximated by linear model, which means that the relationship between x and y is actually linear. 1 unit increase in x will increase y by beta unit, okay? And the relationship is linear, then an approach such as linear regression will likely work well. And it will outperform methods such as a regression tree that does not exploit this linear structure. However, if there is a highly nonlinear and complex relationship between the features and the response, then the decision tree might outperform classical approaches. However, whenever you want to do this modeling, it is good that you try many models, because one thing is you need to know the underlying assumptions between the relationship between the x and the y variable. And if you're pretty sure that the relationship is actually linear, then you use the linear regressions. But if you think that it might not be linear, then you can run any other methods, and then you make the model comparisons to see which one yield the highest prediction. Okay. So what are the advantages and disadvantages of a decision tree? Okay, so one of the advantages, and I would say the main advantage of a decision tree, is it is very easy to explain to people. And some people believe that decision trees are more closely mirror human decision making than do the regression and classification approaches. And trees can be displayed graphically, and it is easily interpreted even by non-experts. You just have to look at the tree and you see that, oh, this is the important variable that is being chosen, and this is how a decision is made, whether this particular observation belongs to this or that. Okay, you can see the rules, the splitting rules very, very clearly. So trees can easily handle qualitative predictors without the need to create dummy variables. Okay. And trees generally do not have the same level of predictive accuracy. Okay, so this is the disadvantages. It might not have the same level of predictive accuracy as some to other regression and classification approaches. And another disadvantage is it is non-robust. Non-robust means that it is not reliable. Any small changes in the data can cause a large change in the final estimated tree. So it can be that you and your friend are using the same data sets, but you remove 5 observations, your friend remove 5 observations on random. And both of you, even though the large part of your data is actually the same, there is a possibility that both of you is going to get a very different result for your decision tree. So that is why we say that it is non-robust. However, the solution is by aggregating many decision trees and using methods like bagging, random forest, and boosting, the predictive performance of the trees can be substantially improved. So in the next section, we are going to discuss ways to improve predictive performance of trees. And the methods that we are going to discuss includes bagging, random forest, and boosting. So let us now start with bagging. So we know that decision tree suffers from high variance and it is non-robust, which means that if you split the data into 2 sets and then you run the decision tree on both sets, it could be that you get a very different results, even though you know the data actually comes from one data set. So we know that the procedure with low variance will yield similar result if we apply it repeatedly to distinct data sets. And this is what we want. We want to build a model that is, that is good enough that it can make a high predictive performance. But at the same time, we do not want to have a model that is complex enough that it overfits the training data sets and it will perform poorly on a new data sets. So some examples of the procedures that we can do includes the bootstrapped, aggregation, and bagging. And how to reduce variance, hence increase the prediction accuracy. What we can do is we can take many training data sets, and from these many training data sets, we can build separate prediction model each, and then we average the resulting predictions. But this is not practical because usually we do not have access to multiple training data sets. So what we can do is we bootstrap. We take repeated samples from the single training data sets. So from one training data set, we take repeated samples again and again, and this process is called bootstrapped. So what we do is we generate B different bootstrap training data sets, and then we train our method on the B bootstrap data. So let's say B is equal to 5. So what we have is we have B bootstrap data, and then we run this method on this data sets and we average all the predictions using the formula given here. So the formula is given by 1 over VP, which shows that it takes the average of all the different bootstrap data that we have. And this whole process is called bagging. And bagging has been demonstrated to give improvements in accuracy by combining hundreds or thousands of trees into a single procedure. Okay, so far the bagging procedure that we have discussed is for regression tree. How about bagging for classification tree? So for a given test observation, we record the class predicted by each of the B trees, and then we take the majority vote, the most occurring class among the B predictions. So how about the test error rate by using the bagging methods? So to estimate the test error rates, we use the out-of-the-bag observations, so OOB observations. So here, just like the analogy is like dividing the data into training and testing data sets, but here we call OOB because there's a distinct procedure involved here. So let's say we divide the data, 2/3 of the data goes to training and 1/3 of the data goes to OOB observations. What we do next is we try to predict the response for the ith observation using each of the trees in which that observation was OOB. So if this observation is not involved in any of the, training data sets that you use to build the tree, then we're going to predict the response for this particular observation. So this will yield B over 3 predictions for the ith observation. And then to obtain a single prediction for this particular observations, what we do is we average the predicted responses in the case of regression tree. Or in the case of classification, we take the majority vote. And then from here, for the regression tree, we can compute the MSE for this OOB, or in the case of classification, we can compute the classification error. So we know that bagging can improve the accuracy compared to a single tree. But then it's going to be very difficult to interpret the resulting model because it doesn't look like a decision tree anymore. Because in the decision tree, it's easy for you to see from the from the first node to the terminal node how the splitting rule is shown. But when you combine multiple trees, it is going to be difficult to interpret the resulting model, and it's no longer clear which variable are the most important. Because it might be that the first tree having x1 as the most important variable, but for the other three, x2 is the most important variable. However, we can obtain an overall summary of the importance of each predictor, and this is different depending on the responses, whether you have numerical response or you have categorical response. So in the case where you have a numerical response, for a regression tree, the variable importance is computed using the mean decrease in the Gini index, which is expressed relative to the maximum. And then we record the total amount that the RSS is decreased due to splits, and then we average over all the B trees. If you have 1,000 or hundreds, then we average over 1,000 or hundreds of the trees. So a large value indicates that this is an important predictor. And for classification tree, we add up the total amount that the Gini index is decreased by splits over a given predictor, and then we average over all the B trees. To give one example on how a random forest works, suppose that there's one very strong predictor in the dataset, and however you want to build the decision tree, and no matter if you split the datasets into many parts, you're going to end up having this one predictor as the most important predictor in the datasets. So in the bagging methods, most of the trees will use this strong predictor in the top split. Consequently, all of the bagged trees will look quite similar, and thus they are highly correlated. However, the random forest overcomes this problem by forcing each split to consider only a subset of the predictors, which is M out of the full P predictors. So in other words, let's say you have P number of variables. Let's say P is equal to 10 number of independent variables. So what you do in the random forest is that instead of considering all the P equal to 10 variables in the first split, you only consider M, which is a subset of P. And in practice, M is approximately the square root of P. Okay, so if you have like 10, then the square root of 10 is about 3. Okay, M is equal to 3. You only consider 3, a random 3 predictors. So this will avoid from a highly correlated trees in the random forest. And the last technique that we're going to talk about is boosting. Well, boosting works like bagging. The algorithm looks like bagging, except that the trees are grown sequentially. So each tree is grown using information from previously grown trees. Well, boosting does not involve bootstrap sampling. So each tree is fit on the modified version of the original data sets. So given the current model, what we do is we feed the decision tree to the residuals from the model. It's like a feedback mechanism to tell us what went wrong or what went right. So when we add this new decision tree into the fitted function in order to update the residuals, and that process is called boosting. So that's all for now. So to use the tree function, we have to install the package tree, and then I'm going to load the library tree, and then the library of ISLR for the datasets. and the data sets that we're going to use is the car seats data sets. And I think it is useful if you can run some functions like dim of car seats. So we know that we have 400 observations and 11 variables, and I just want to type in names of car seats. So these are the 11 variables. We have sales, we have comp price, income, advertising, population price, chef lock, age, education, urban, and US. So here is, if you want to know more about these data sets, again, we just type in question mark car seats. So we know that this is the data sets on the sales of child car seats. And this is a simulated data set containing the sales of child car seats of 500 different stores. And these are the informations on all the variables that you can read. Okay, but we are interested in looking at one particular information, which is the sales. Okay, so the sales here is the unit of sales in thousand at each location, and sales is actually, if you type in STR of car seats, you can find that sales are actually numerical. So here is, because I want to show you how to build a classification tree. So we actually change this variable this variable sales into category. Okay, so we're going to create a dummy and we're going to name it as high. And here I'm going to use the function if else. So if else, so if sales is less than or equal to 8, then we're going to categorize it as no. So if sales is larger than 8, then it's going to be yes. Okay. And the next line, what I do is actually I include this newly created variable into this car seats data sets. Okay. So if you run the dimension just now, you know that originally we have 11 variables. But here, if you run dim again of car seats, the new variable high is already included, and now we have 12 variables. Okay, so you can run the str function just to check. So the variable high is actually a factor with 2 levels, so you have no and yeses. Okay, next is we're going to run the tree function here, and we're going to name this tree as tree.carseats. So this is the name of the decision tree that we have. And remember, this is a classification tree. And there's no difference between the functions for classification and for regression tree because they are both the same. We just use the function tree here. So this is the tree where the response variable is high, and this is category. And this is like, run on the rest of the variable. And here we have minus sales. Okay, why do we have minus sales? Because sales actually is the same information as high. The variable high is created from the value of sales. So if you put sales there, it's going to be a perfect multicollinearity, a perfect collinearity with the response variable. So we remove sales. So the dot means that we include all the variables, and minus sales means that we remove the sales from our calculation here. And then we comma, and then we have the name of the data sets, which is car seats. Okay, so all of the results for the tree function here is stored in tree.carseats. So now let us extract one of the informations that we have in this tree.carseats. One of it is the summary. So the summary is just a summary for this classification tree. So first it will tell you that this is a classification tree because your response variable is category. And the next line shows you the formula. So this is the formula that you give to R. And next is we have the variables actually used in the tree construction. You can see that among the 10 variable, you actually use 8. Okay, and these are the 8 variable that is being used. And the next line shows the size of the tree, which is 27. So this is the number of the terminal nodes in the tree. So you have quite a big tree here. And next is we have the residual mean deviance, and here we have mean deviance because this is category. And lastly, you have a misclassification error rate, which is 0.09. So this is 36 of the observation is wrongly predicted. Okay, next is what is the most interesting thing is that we are able to plot this decision tree. So you just run the plot function. So if you just run the plot function, it will give you the structure of the tree. Okay, with 27 terminal nodes, you can count. And next is we run the next one, which is the text. The text of the tree.charseeds, and here we have another syntax here, which is pretty equal to 0. So pretty equal to 0 is for, let me check again because I can't really remember. So pretty equal to 0 includes the category name for any qualitative predictors, any categorical predictors rather than just the letters. So of course, if you look at this one, you can't really see it, so you have to zoom in so you can see more clearly. Oh, I'm afraid when I try to zoom in, it doesn't appear in the, it doesn't appear in the video record that I try to record here. So unfortunately, I can't show it to you. But what you can do is you can just click on this zoom and you can see. Okay. So you can enlarge this zoom, plot to see. And here we have the most important variable is the chef log. And then after that, we have the price, and then we have the advertising and so on. Okay. So at the terminal node here, what you have is the no and the yeses. So the no and yes is the predicted value for the response variable. Next is if you try to run the tree.charseed itself. So what is the next is what is going to happen. So it's going to print all the splitting rule for each of the terminal nodes. So in total, you have like 27 here. Okay, not only the terminal node, but I believe the internal nodes as well. So let's look at the first one. So the first one is the parent node, which is at the top here. You have the root node, and in this root node, okay, let's look at how it is it reads. Okay, so first is you have the number for the node and then close the bracket, and the next one is you have the split. So what is the variable that is being used for the splitting rule here? And then you have the number of observation, and then you have the deviance, because again this is a classification tree. And then you have the predicted response for the y variable, and then you have the probability for the response variable. Okay, and the star denotes the terminal node. For example, like the star for the node 16 here. So this is the terminal node of the one terminal node, and then this is another terminal node. So if you look at the beginning, so this contains all the internal and the terminal nodes. At the beginning, we have the root node, and we have all the 400 observations here. And then we have the deviance, because this is a classification tree. And this is the predicted y value. So we predict it to be no. And this is the proportions of being a no, and which is 59%, 59%, and the remaining 41% is the proportions of yes. And then we look at the first internal node, which is the chef log. And here the chef log, actually, if you try to run contrast of chef logs, you can see that it contains 3 levels: bad, good, and medium. And in this case, we group the bad and the medium into one group. So on the left hand side, we have bad and the medium, and here we have 315 observations, and this is the deviance. And there's a high proportions of this. If you have a bad and a medium chef log, 68% probability that it's going to be a no. Well, there's a 31 probability that it's going to be a yes. But for this one, if you're chosen here, then we predict it to be no. Okay, but in overall, we are most interested in looking at the terminal node here. So the terminal node shows that if the chef log is bad and medium, and then you look at the price, and if the price is less than 92.5, Then we look at the next one. If the income is less than 55, and then you look at the comp price. Okay, so if the comp price is less than 110.5, then we predict it to be no. But if the chef log is bed and medium price is less than 92 and income is less than 57, but the comp price is more than 110.5, then we predict it to be yes. If you look at the proportions here, the proportions of yes is also higher. So of course, it is quite difficult for us to just look at the rules here. So that is why we have to look at the, diagram. But unfortunately, in this video lecture, I'm not able to show you the zoom video of this one. So what you can do is you just have to, just click on the zoom and you can see the rules more clearly. Okay. So next is we want to estimate the test error rate to evaluate the performance. And for this one, we will divide the data into two. So one is the training data sets, another one is the testing data sets. Okay. So first is because I want the result reproducible, so that whatever result that I have, you'll also have the same result. So let's use the same set.seed. Here set seed of 2. And the next line is I create a training data sets, and here I use the sample function. So the sample is from 1 to the number of row of the car seats, which means that the number from 1 to 400. I want to make a random sample of 200 data sets. So here we have 50% data sets belonging to the training data sets, and the remaining will be belonging to the test data sets. So next is, first is the training data sets, and the second one is the carseat.test is equal to, we try to copy whatever is in the carseats data sets, and here on the row part, we put that the minus train, which means that we remove all the training data sets. Okay, and here is we create a new vector, hi.test, and hi.test is copying the hi minus the train, and then we're going to build the decision tree based on these training data sets, in which we have the same name actually, tree.carseats equal to tree, and here we have hi, and it is built on all the other predictors except sales using the carseat data sets, but now we have a subset equal to training data sets. So if you look at the lecture notes in the lab sessions, right, you can see that I do this in many ways, not just one way. Okay, sometimes I created a training data sets, and I, a new training data sets. Sometimes I use this subset equal to train. Sometimes I use the sample here. Sometimes I use different methods. So this is just to show you that there are many ways of doing the sampling or doing the division between the training and the testing data sets, and also there are many ways of introducing the training and the testing data sets. So this is one of the ways. Okay, now we have built this tree based only on the training data sets, and we save it in tree.carseats, and next is we're going to predict. So we predict using the predict function here, and the result from the predict we store in tree.pred. Okay, so here is what we predict. We predict the tree.carseats based on the carseats.test. Okay, we predict the carseats.test based on the model of tree.carseats, and the type is class because we have a classification tree here. So we want to predict what would be the class for this variable, or for this observation. Is it going to be no, or is it going to be yes? And finally, we have made the predictions. Let's just show the first few of the observations. So the first few is the first observation you predicted to be no, and the second one is yes and no, 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 and yes. Okay. So finally is we build this confusion matrix, or the classification table, and we can see that on the row part is the predicted value. We predict this to be no, and we predict this to be yes. and on the column part is the actual value. Okay, so from here you can actually compute the misclassification rate. So the prediction accuracy here is given by 86 plus 57 divided by the overall observation, which is 200. So we have 71.5% or 0.751. So now let us consider some pruning and see if it might lead to improved results. So for the pruning, we will use the CV.tree, which is the cross-validation to determine what is the optimal level of the tree complexity. So first is we use the same set.sit, which is set.sit of 3, and then we're going to use the function cv.tree on the tree.carsits model that we have developed just now, and we're going to store this into cv.carsits. So this is the cross-validation for the carsits. First is we're going to find out what is the optimal size, optimal number of the size of the tree. And here the function is equal to the prune.misclassification, because this is a classification tree. So we want to make this cross-validation based on the misclassification instead of the errors. Okay. So first is, because we have run this function, the cv.tree function, we want to know what is stored in the cv.carsits object. So here we have size, we have div, which actually stands for deviance, but the name is deviance, but since this is a misclassification, so this is more like the error. And of course we want to have a minimized error. And K here is actually the cost complexity pruning alpha that we cover in the lecture just now, the alpha, and also the methods. Okay, so now let's just run the cv.carsits and see what is in there. So here the objects are stored in terms of the list. So the first list is the size. So this is the size of the tree. And this is for the first cross-validation, we get the size of the tree equal to 19 and 17, 14, and so on. And now this is what we are interested in looking at. So this is the error, okay? And we want to have the minimized error, and we can see that the minimized error is actually the number 1, 2, 3, 4, and 5. Okay, so the fifth one here corresponds to the size of the tree equal to 9. Okay, and the corresponding cost complexity function is 1.75 here. And okay, so we would say that it might be better to have the size of the tree equal to 9 instead of just now. How many? What is the original size of the tree? Okay, we have to go back to the result that we obtained just now. Okay, so the tree with 9 terminal node results in the lowest cross-validation error rate with 50, okay, with 50 cross-validation errors. So next is I'm going to show you the cross-validation results first. And first is I'll run this line to change the graphical parameters to contain 1 times 2 dimension. So first is I'm going to plot the cv.carsits of the size. So this is between the size of the tree and the error, okay, the cross-validation error. And the next one is the plot between the cost complexity pruning and the error. Okay, but we are particularly interested in looking at the left-hand side. Okay, as you can see, the error actually minimizes when the size of the tree is equal to 9. So we will say that the optimal number of the tree is 9 to reduce the cross-validation error. So now we create a new pruned tree, the tree that has been cut. So we name it as prune.carsits. So this is equal to prune.misclass. We use the function prune.misclass for pruning the tree. So we want to cut the tree from the tree car-seats, where we want to have the resulting output should have 9 terminal nodes. So best is equal to 9. And next is I change the graphical parameter again. And now I want to plot the pruned tree, the tree that has been cut to only contain only 9 terminal nodes. So if you can see here, the structure of the tree only contain 9 terminal nodes. And next is we want to run this text to show the labels for this tree. Okay, so in the end, this is the tree that performs the best, where there's only 9 terminal nodes. Okay, so the next is we want to know how well the prune tree perform. So just now, if you look at the original one, we have the predictive accuracy equal to 0.715. So for this prune tree, if we can have higher than this, remember this is not misclassification. This is the correctly classified proportion. So 0.715 is quite high, which is very good. But we want to see if the prune tree actually give a higher proportion. So again, we predict based on the testing data sets. So we predict the prune car-seats based on the testing data sets. And again, type is equal to class because this is a classification tree. And then we're going to tabulate between the predicted and the actual value. And we get that 94 plus 60 are correctly classified. So 94 plus 60 over 200 is 0.77, which is higher than the previous one, which is 0.715. So we would say that the prune tree, the tree that has been cut down to size equal to 9, perform better than the original tree with 27 or something terminal nodes. Okay. So what if we want to try to increase the number of the terminal nodes? We want to have 15 terminal nodes instead of just 9. Okay, you want to have a more complex model. So here we just run it again, but this time we prune the classification tree to contain 15 terminal nodes. And then first is I'm just going to show how the decision tree looks like. So it looks more complex compared to having only 9 terminal nodes. And then we make the prediction and we tabulate the actual and the predicted value. So this time we correctly predict 86 plus 62 compared to 200. So actually the predictive accuracy is 0.74. So in summary, even though we increase the complexity of the model, but we suffer in terms of the predictive ability. You have a more complex model, but you have a lower predictive ability here because previously we have run the cross-validation and it shows that the decision tree with only 9 terminal nodes actually perform the best. Okay, in the next exercise, I'm just going to show you how to fit the regression tree using the Boston datasets. Well, actually, this is much simpler than the previous one. So here we have to load the library mass because the Boston datasets comes from the package mass. And to maintain reproducibility, we use the set seed equal to 1 here. And then we create the training datasets, which is using the sample function. So from 1 to the number of row in the Boston datasets, and then we want to make how many observations in the training dataset. So basically, what is n row of Boston? I'm not sure how many datasets in Boston datasets. So we just going to compute. So based on the n row of Boston, which is 506. So we're going to select half of it to become our training data sets. Okay. And here we use the tree function. Again, I told you that the tree function can be used for both classification tree and also regression tree. So you just put that and it will automatically assume that this is a regression tree if the response variable is numerical. So this MADV is run on all the other variables using the Boston datasets, where the subset is the training datasets. And again, we just run the summary. We see that the variables that is being used in the tree construction is just three variables, THREE. And there are 8 number of terminal nodes. So the size of the tree is equal to 8. And we have the distribution of the residuals, okay, because this is a regression tree. And again, we can use the plot function to just show how the tree looks like. And then I'm not sure why it is not really working. So there's something wrong with my computer. So this computer is more than 10 years old, so sometimes, you know, it pauses without any reason. So this is how the regression tree looks like. Again, you can click on this zoom to see more clearly, but since I can't show you this one, so I have to stick with this. So the most important variable is the LSTAT, and then we have room, and we have this, okay? So all these three that is being listed here. So again, you can just type in tree.boston just to show how the split rule looks like, okay? So here we have how many terminal nodes. You can look at the summary here. There are 8 terminal nodes, and it is denoted by the star. So there are 8 stars here. So the first one is this one, number 16, which corresponds to this one. So if we have like, okay, let me pick something that is easier for us to see, okay? Let's look at the right branch here. If LSTAT is higher than 9.7, and you go to the next one, and if LSTAT is actually higher than 21, then we predict the response to be 11.10. Okay, so you can see that it is node 7 here. So LSTAT is higher than 21.49, and we predict the value for the y, which is the mean of the response variable, to be 11.10.